Let us evaluate this very famous, very popular, very well-known integral, the Gaussian integral. Now, this is one you will encounter in many contexts like statistics and physics. It is a very important and very useful integral. And if you don't already know, it evaluates to, spoiler warning, the square root of pi over a. Now, you might look at this integral and you look at the result, and it's not really intuitive how you come up with that conclusion. In this video, I'm going to explain in the simplest way possible how to get to that result. Now, because I cannot analytically evaluate this integral, I have to get a little creative with how I solve this. What I'm going to do is I'm going to first give this integral a name. It does not matter, it could be any variable, any name. I'm going to give it this name. It is a heart, because I can. And I'm just going to rewrite that integral. It's the integral from negative infinity to infinity of e to the minus ax squared dx. Now, because I have free will, and this is going to benefit me in the next few steps, I am going to square this integral. So instead of having one heart, I am going to have two hearts. So I have the integral from negative infinity to infinity of e to the minus ax squared dx. And then I have another integral of negative infinity to infinity e to the minus a pause. Now, I can technically name this integral or use the variable x in the second integral too, but that is kind of stupid, and x is a dummy variable, so I don't really need to stick with it. And I could just define a new dummy variable, in this case y. A common theme that you will notice throughout this specific analysis is that variables don't really mean much. They're interchangeable, they are not permanent, and they're there for convenience. So now that I have two integrals, I can combine them. So I have the integral from negative infinity to infinity, and then another integral from negative infinity to infinity. I have my two exponents. One is from negative, or e to the minus ax squared. The other one is e to the minus ay squared. And then my two differentials, dx and dy. Now, two exponents is just too much for me, so I'm going to combine them into one using some algebra and what I know about exponents. I'm going to factor out the minus a term, and so I have x squared plus y squared dy dx. Sorry, what did I name this? Sorry, it's dx dy. Dx dy. Great. Why did I do all of this? So just go back for a second. So I started with one integral with one variable, and now I have two integrals with two variables. Why did I do that? What benefit does this serve? Well, if you look at this specific term, you might be thinking of something, it might ring a bell, and you might be wondering, or you might be thinking to yourself, can I define this as a new variable? And yes, you can. Matter of fact, you could change this entire coordinate system to another one that will help us. You could change this to polar coordinates. So if you say x squared plus y squared is r squared, and redefine your entire integral to fit polar coordinates, this is gonna make evaluating the integral even easier. So let's switch to polar coordinates. Now, because I'm including all values in my integral, I'm going to include all values in my polar coordinates as well. So now my integrals evaluate from 0 to 2 pi for theta, and then 0 to infinity e to the minus a r squared, because this is r squared as we said, and then the Jacobian for polar coordinates has a copy of r dr. Now, because I have there's really nothing to evaluate in terms of theta, this is just going to be 2 pi. And then the only thing I really have to work on is this piece, the integral from 0 to infinity of e to the minus a r squared, r dr. This is actually doable, finally. I can actually do something. And the thing that I'm going to have to do is, from my old toolbox of integration friends, u substitution. I'm going to define u as ar squared. So the du is 2ar dr. And then to match what I have in the integral, I have 1 over 2a du is equal to r dr. And because this is just a constant over here, I'm going to take that outside of the integral to make my life even easier. So I have 2 pi over 2a, and I'm evaluating the integral now in terms of u. So of 0 to infinity of e to the minus u du. And now I could finally get rid of the integral. I could actually integrate this. So I'm going to keep my constant and I'm going to simplify this outside. This is pi over a. And then when I integrate e to the minus u, there's a negative sign that comes out of it. So I'm also going to factor that out and take it outside. And now I am evaluating e to the minus infinity minus e to the minus 0, or just e to the 0. So e to the minus infinity is 0. And then e to 0 is 1. And because I have a negative sign here, this goes outside and it cancels with this negative sign. So I'm left with pi over a. We're almost done. We just have to remember that I squared my integral over here. So I have 2 hearts. So this is equal to a squared. So then if I take the square root on both sides, heart, which is equal to square root of pi over a, is equal to the integral from negative infinity to infinity of e to the minus ax squared dx. And that's it.